Hello, everybody. This is Andy Ellicott from Swarm64. I want to thank you all for joining us today to learn about hardware acceleration options for Postgres. Before we get started, I wanted to cover a few logistical points. Today's event should last about 30 to 45 minutes. We'll have question and answer at the end. If you have questions as we go along, please type those into the questions panel and go to webinar at any time during the event. And we'll get to as many as time allows after Thomas and Skip present. We will also, since one of the most common questions is, can people get a copy of the slides? The answer is yes. We will share a copy of the slides and recording of the event with everybody via email after the event concludes. So look for that either late today or early tomorrow. Our agenda today. We're going to talk a little bit about the hardware accelerator market growth and why people should start caring about hardware accelerators for database performance. I'm going to turn things over to Thomas Richter, CEO and co-founder of Swarm64, to talk a little bit about the different types of hardware accelerator options that are out there and how they can potentially impact database and be applied to database performance. Specifically Postgres, and then I'm going to turn things over to Skip Moorhead, who's head of technical services at Swarm64, who will go on a bit of a deep dive to talk about how one would sort of apply FPGA to their Postgres implementation. As I mentioned, we'll conclude with questions. Okay. All right, so why are we talking about hardware accelerators and what are hardware accelerators? And if you've been following either companies like Xilinx, NVIDIA, makers of GPU and FPGA, Intel, you'll know that they've been pretty hot stocks lately. And if you follow artificial intelligence, machine learning application, kind of data science, you know that those types of workloads require a lot of parallel processing and really driven up the demand for these new hardware accelerators that are very popularly applied to artificial intelligence workloads in data centers and on the clouds. So we're talking about GPU, graphic processing units, tensor processor units, which is unique to Google, processing TensorFlow applications, FPGA, field programmable gate arrays, which has been around quite some time. That's really what Swarm helps people apply to their Postgres implementations. And then application-specific integrated circuits. Really a lot of investment and new companies popping up with specialized chips for, again, mainly processing artificial intelligence workloads. So we're going to talk mainly in this presentation about GPUs and FPGAs and how they compare to CPUs. Thomas will go through that. But again, if you're on the cloud, you probably noticed that Amazon, all the cloud providers offer GPU accelerated instances. AWS and Azure both offer FPGA instances. If you go back far enough in the database business, you might remember a company called Netezza, which IBM bought and has since been end of life. But they really invented the idea of the data warehouse appliance about 10 or 15 years ago, and kind of famous for applying FPGAs to database, to Postgres specifically inside these appliances to really revolutionize the economics of data warehouse implementations. And so again, with these special hardware accelerators becoming more accessible to you, more affordable, I think the point of today's, hopefully the takeaway from today's event is that, whether you need to scale up or scale out, considering you ought to take some of the accelerator-equipped servers into consideration, because they might be able to, make the scaling easier and again more economical. All right. So with details on the accelerators, I'm going to turn things over to Thomas Richter, who co-founded Swarm64.
Yeah, thanks, Andy. So I will basically be covering a little bit of the differences between CPUs, GPUs, and FPGAs. Now, disclaimer to start with, there's a lot of devil in the details. So this is going to be a fairly broad overview. And of course, it includes a lot of simplifications. So if you find that the one or other thing is maybe described in a too simplistic fashion, number one, you're of course more than welcome to ask questions here in the panels. And also, number two, you know, in the interest of keeping it an overview, I had to display some things a little more in broad strokes than being able to go into all the fine details. Sorry, so with that, let me just go on to the general overview of our good old CPU. So the CPU, I mean, this is really the reference point, right? Whatever accelerator we're measuring against the CPU, because that is basically the universal resource in every server, and that has certain characteristics. And one of the key things, it is basically excellent at executing pretty much anything computer, right? Like serial programs, the standard way you code, the standard way you would have your software behave, that is what a CPU was made to do. And it therefore gives you the greatest flexibility. And in modern systems, it's very easy to scale to terabytes of RAM. And with modern systems, you have at least 6 memory channels per socket in a server. And each channel will give you roughly 15 gigabytes per second real-world performance. Of course, they're rated to give you much more, but this is really for streaming workloads. So when you're looking at kind of standard performance, you're looking at 15 gigabytes for every single channel. And then you have these AVX registers that are basically little, you could argue, little mini GPUs inside a CPU. You have registers and processing logic that allows you to do a single calculation on, for example, 8 values at the same time. And this then allows you to execute certain processing quite quickly and quite efficiently. So in a way, CPUs already have multiple degrees of parallelism. One of them is, of course, there's many CPU cores in a socket. And on the other hand, every CPU core has, again, AVX registers and AVX processing logic to be able to have single instruction, multiple data kind of flow. CPUs are easy to debug, and the database management, relational database management systems have been running on them for pretty much forever. And the nice thing is, if they are CPU bottlenecked, a new generation of CPUs usually gives you a performance gain, and that can, again, if it's a CPU bottleneck, pretty linearly translate to a acceleration of your database. So this is really the reference point we are measuring all other architectures against. Let me flip over to talk a bit about GPUs. So GPUs are quite different beasts from CPUs because they were, of course, originally made to process graphics. And quite specifically, the part of a GPU we use nowadays is derived from the pixel shading logic. That was basically a logic designed to process every individual pixel on the screen, and to do so with a very high degree of parallelism, because as you can imagine, the pixel shares a lot of similarities to the pixel next to it. So you can process pixels in parallel, and this is exactly the kind of logic that is still pretty inherent to how you process on GPU. So they call it a single instruction, multiple threads. In other words, you're basically doing the same thing, but you're doing it on many different contexts. So again, I'm going back to my pixel example. As you're shading a pixel, you're always doing the same steps. For example, look where the light comes from, retrieve what original color this pixel should have, and calculate the mixture of the lighting and the original pixel color to find the actual color on screen. And the same you can do for computational programs. You can basically process the same logic in multiple threads, one for every individual piece of data. That gives you very extreme performance. And in order to fuel such a performance, those GPUs generally also have a tremendous amount of RAM bandwidth. So they have generally GPU RAMs or high bandwidth memories that are connected closely, and they can give you things like 0.3 terabytes per second in real world bandwidth. Yes, on the spec sheet they have even higher numbers, but again, we're talking about real world bandwidth here. That means that very quickly interfaces become the bottleneck. And you see examples of that. For example, NVLink from NVIDIA is one of the interfaces that are used to try to overcome this bottleneck of how do I get data in and out. And in a moment, when we're looking at how GPUs can accelerate databases, we are looking at two different ways of how you can actually get data in and out. They're limited RAM. Because the RAM is so high bandwidth, it doesn't tend to be the cheapest. Quite the opposite, it tends to be the highest end, and usually it's in the tens of gigabytes. It's difficult to write good programs. It's not too difficult to write a program, but to write a program that uses a GPU well actually requires a lot of detailed understanding of how a GPU works. And it is actually much more difficult to debug than a CPU. But it is quite possible to debug it. And there's not so many relational database systems that actually benefit from a GPU. And the reason for that is that you really have to rebuild it from the ground up. The GPU typically exposes quite cruelly any bottleneck you may already have in your system. So you have very little leeway for existing bottlenecks. Otherwise, the GPU sits there idling. So we see, yes, there's some projects around GPU acceleration of existing things. One example is, for example, PG-Strom, which is GPU acceleration of Postgres. However, generally, those programs that can use GPUs best are the databases newly developed for GPUs. And finally, the raw performance is highest in its class, and in principle, this parallel processing I was describing earlier is very well suited to databases. In principle, I'll get to it in a second. So let me just move to the next slide. Now let's look at an FPGA. So an FPGA, on the other hand, is entirely different. I mean, it's being occasionally compared to GPU, but that is more to give people a frame of reference. In reality, FPGAs are coming much more from, for example, prototyping specific purpose chips. An FPGA is really a blank sheet of paper. It can turn into any logic, and therefore you can best think of a configured FPGA as a special purpose chip. However, this configuration is actually something that is very transient, as in it is configured on the FPGA and then in 1 to 3 seconds later, you could apply a different configuration. So you can actually upgrade hardware without any physical touch. It's a little bit like the Tesla cars that download a new firmware and then next time you enter your car, suddenly your car has a new capability. That's very much how we can imagine FPGAs in a data center. You can provide upgrades to it without going anywhere close to the box. And FPGAs are extremely complex to develop for. So whereas it is entirely realistic that you would have in a company a custom development for CPUs, that's totally normal. Everybody has some custom code, even if they're not necessarily a software company. It's quite rare for companies that are not software companies to do anything on GPUs. And is actually utterly rare for a company that is not deeply ingrained in hardware design to do something for FPGAs. So the important part is really, and Netezza is an example of that, is to use the power of FPGAs wrapped into a product. That's the crucial thing. And Netezza has done that, has basically built backplanes with FPGAs that filter the data. And just to conclude on that slide, the key thing is can execute any logic, and that makes it more versatile in terms of adjusting it to what's already there. So in order to extend proven solutions, you're able to fill the logic on the FPGA with things that are specific to what you're trying to accelerate. So whereas in a GPU context, you would probably design your database around what the GPU can and cannot do. In an FPGA context, it's much more flexible because there the FPGA can be what it wants to be, and you can really co-design database and FPGA. So let me move on a bit, and now I'm going to talk to you a little bit about how data is processed inside a database. Again, disclaimer, it's a simplified view. Let's look at a standard row store database on a CPU. You have a plan that is usually not overly parallel because, quite honestly, row store databases generally tend to look at something called the index to specifically retrieve where data is. Then you have specific data points that you're retrieving from your table. You've actually picked out rows that are belonging to your result set. You're then picking individual columns from these rows depending on the query, right? The query conditions will determine which rows you pick, and then you get to a result. So that's kind of database, grossly simplified database 101. Now let's look at how you would process in a more analytical context on a database. And again, when we're talking database acceleration, we're mainly looking at analytics. In fact, the predominant part of the hardware accelerated databases is in the domain of analytics. And that has a very simple reason. There's always some delay introduced to move data to any form of accelerator. And in a transactional workload where it is about seconds or milliseconds of execution time, then you would not want to encounter that additional movement. So when you're trying to process analytics on a classical database on a CPU, you would not take the row store that I gave the example of earlier. You would basically look at a column store. So a column store is basically data layout optimized for analytics. You could keep these columns in RAM, then you would be looking at an in-memory database. You could keep them on disk. That is entirely depending on the implementation. You start with a very parallel plan. It's crucial that you're actually processing a lot of data in parallel. You will find out in some shape or form which columns are actually pertinent to your query that you need to load. You would scan these columns. You would pick the fields from these columns, all that in accordance to the conditions from the queries. You would recombine these fields back into rows, and you would end up with your result set. So that is a columnar processing on a CPU. Let's look at two examples of how people do columnar processing on GPUs. So number one is GPU in memory. That is a concept that is used by which data resides in GPU memory. That comes with a benefit and a drawback. The benefit are those tremendous memory bandwidths we've been talking about earlier. The drawback clearly is that you're limited by the amount of memory you can have. So it's basically creating a thread parallel plan that is very, very highly parallel. It then scans the columns directly. They're already in GPU memory, so there's no data movement or anything. You can just scan the columns that are pertinent to the query. You pick the fields, all of that in parallel, thanks to the parallelism afforded by the GPU, assemble the fields into rows and return a result. Very fast, but very limited in its data set size. Now there's another concept in the market I've labeled here GPU streaming. You start with a parallel plan. It's usually not as extremely parallel as in the previous example, quite simply because the bottlenecks are usually somewhere else. The GPU has tremendous performance, but in these examples where you're actually streaming data into the GPU, you tend to encounter different bottlenecks, and therefore it's not so crucial that the plan is as parallel as in the previous example. You stream the columns into GPU memory, and then you scan the columns in GPU memory. And you pick the fields and apply all your conditions in GPU memory, fields combine to rows, and you go to the result. The benefit here is you have a lot more data, and basically your data is in theory unlimited, because as long as you can stream data into the GPU, you can process this way. The drawback clearly is your processing is not the bottleneck. Instead, your data movement becomes the bottleneck. So you're not using your GPU to its maximum potential. So let's now look at hardware accelerated queries inside an FPGA. And that's just one example of how you do it. This is very, very close to what Swarm does. This has probably some resemblance of what Netezza does or did, simply because there's certain design principles that make sense on FPGAs. So you have a parallel plan. Again, parallel plan is absolutely crucial. You're basically running a decompression on the FPGA that is enabling you to move data quickly. So one of the ways in which you want to avoid interfaces becoming the bottleneck is by allowing to use and work on compressed data. And then once you've decompressed, you would pick columns, you would pick rows from these columns, again, everything in accordance to the query that was provided, and then you get to the result. So a little bit different process there than your typical column store. And it has a few advantages that we'll get to later in the presentation. But in broad strokes, that's the difference between FPGA, GPU, in-memory GPU streaming, and the CPU. Now, let me just give you an example on what the FPGA could look like when you apply this to a standard benchmark. This is some measurements we did. This is already a version that is one version behind. We've been improving our performance since. And you see that in Postgres, so on the one side you have Postgres, on the other side you have an FPGA accelerated Postgres, that's in orange. We give about 6 to 7x performance benefit at a very small TCO increase. So let's go back to a quick summary. So on the processing side, the CPU kind of sits right in the middle. It's giving you what you're used to, your standard processing methodologies, but it doesn't have that extreme raw parallelism that GPUs can offer. An FPGA is very difficult to put into category because it's entirely reconfigurable. So when you're looking at that kind of data flow I was describing earlier, basically you would always reconfigure the FPGA in order to match the bandwidth. So processing in terms of units or in terms of capabilities isn't really the right measure. It is applying the right design on the FPGA that it can perfectly match the bandwidth. Now, on the memory, of course, the CPU has the highest amount of memory available. For in-memory GPUs, you're actually looking at, this is the lowest amount of memory available, because for streaming and for FPGA streaming or GPU streaming, memory doesn't really matter. You can basically push in as much data as you like to, and that could come from, for example, CPU memory, that could come from storage devices, it could come from the network, it doesn't matter. All these streaming cases basically are in principle unlimited. Cost is, well, CPUs are reference, so that's our midpoint. Also, GPU streaming or FPGA streaming do not tend to make a huge difference on the overall cost of a system. However, GPU in memory, for the very reason that it's using this extremely expensive, extremely high-speed memory, is actually the highest of the cost factors. How easy is it to adopt into existing relational database management systems? Well, we've already talked about it. They all run on CPUs. So just putting in, for example, a faster CPU is actually the default thing to do. With GPUs, it's actually pretty complicated, as talked about earlier. And then finally, for FPGAs, it can be very easy because the processing on the FPGA can be adjusted to where you would basically, what you would basically want the logic to do. So this is the very essence of reconfigurability. Finally, impact. So the CPU is our reference point. So, you know, the impact that's our standard. That's where we started from. In-memory GPUs, yes, no question, this is the highest performance at the highest cost. And then with GPU streaming and FPGA streaming, you're in both cases looking at a high performance impact, like just shown in the slide before, but of course without some of these difficult compromises that GPU in-memory processing comes with. And that concludes my part of the presentation. So I hope I was able to give you a very, very rough overall overview of how you can process in different ways your database processing, your query processing with these different accelerators, and what choices different vendors have made in the market to process their data.
Thank you, Thomas. So at this point, I'm going to turn things over to Skip Moorhead. As I mentioned before, he's the head of technical services at Swarm64. He's been in the database industry a very long time. Prior to joining Swarm64, he was at Oracle and a bunch of other database companies before that. And he's going to talk about the process of hardware accelerating a Postgres database using FPGA and Swarm64. So Skip, it's all yours.
Thanks, Andy, and thanks, Thomas, for that high-level introduction to the overall problem that we're attempting to solve here, that we do solve with Swarm. But I want to take just a step back a little bit and talk, about some thinking that typically goes into solving these data processing problems. And one of the things that we're seeing a lot of movement and trends towards looking at products that have specific strengths, such as NoSQL or Hadoop or things of that nature, graph databases. And the other trend we're seeing is that folks want to use open source where possible, and we're seeing a huge movement towards open source products being able to supply and provide the different feature functionality that people are looking for. And in fact, there's some pundits and trends forecasting that talks about open sources overtaking commercial databases over the next sort of 5 to 7 years or so. And we chose an open source product, Postgres, because of its ubiquity in the relational transactional market, and the strengths that it provides, such as well-defined interfaces and, again, the whole open source nature. And we see that people are looking at the problems that they're faced with, tend to think about the choices that they have to make. And it kind of boils down to consistency or scale. And what we find is that folks that are looking for like split section reactions are looking for very consistent, transactionally consistent databases that provide a robust environment for inserting and getting data into the database very quickly and consistently, and making that data available to other transactional systems or in moving it into other data sources for analytics. The other aspect to this in the world of streaming data and IoT and all these sorts of things, and where the big data world fits, is that it's the interactively exploring millions of new records per second. Data is coming in very quickly. They need to be able to store that and analyze it, and being able to provide insights into that data starts to become a big part of the thinking process that folks are dealing with. So we find we've done a lot of research. Thomas has been very, part of this from the beginning, and he's done an awful lot of research. At Swarm, we have a whole team that is really dedicated to understanding programming FPGAs and understanding how to optimize the value of FPGAs in this type of environment. We have a whole database team that integrates with the FPGA team and works very closely with that to make sure that we have a product that fits a couple of different angles. And one of the things that we find is that folks are looking for split-second reactions, as I described on the earlier slide, where we potentially want to be able to do transaction and analytics. And one of the values that Swarm brings with the FPGA is the ability to coexist with a transactional system. So the traditional behavior of taking data out of a OLTP system, ELTing it into a data warehouse is still a big target for us, but we also find some value in folks that are looking for doing that hybrid transactional analytic processing, where you need to be able to get rapid access to data that's happening in near real time. The other thing that's important is interactively exploring huge data sets. And as Thomas was pointing out, in the GPU side of things, you typically, in order to get to large data sets, you have to use a different kind of architecture. GPUs really shine when you can fit the whole data set in memory, and you can in the GPU memory, and you can do very fast analytics against that. We don't have that problem. We're really able to support terabyte and petabyte sized databases. And the interesting thing is that we can do this in some cases up to 50 times faster, depending upon the type of queries that you're running. And equally important is being able to store and analyze large volumes of data coming into the system quickly. We've seen situations where we're able to store, 20 million plus new records a second. For example, pulling data off of a network interface, we could do that at line speed. And so these combined with, all the things that we're doing here, combined with the FPGA and the hardware analytics and the Postgres system, gives us a very low TCO to be able to solve very large problems. Equally important is something Thomas didn't mention, is low wattage. And that's important because GPUs tend to be very power hungry. And when you're building out a large system that's in order to support a large data set and large number of users and get the kind of performance you're looking for, it starts to become very expensive, not only from the actual equipment standpoint, but all of the run and maintain stuff. The data center configuration starts to become important as you're architecting these solutions. So we built out a solution on FPGAs that gives you a long-term solution with, on-the-fly reconfiguration and very easy to do hardware upgrades out in the field. We partner with both Intel and Xilinx, and we provide our solution on both of those platforms. And again, we're focusing on Postgres as the core database that we're doing the acceleration against. Next slide, please. So if you look at a fairly traditional data warehouse kind of environment, this is an architecture that probably looks familiar to a lot of you. All the operational data, all of the OLTP type of systems sitting on the left side, different kinds of databases. It doesn't really matter from our standpoint what the database is. It could be an Oracle system. It could be something like MariaDB or MySQL. It could be Hadoop. It doesn't really matter where the data is coming from. We're piping it through a ELT process, and then we're accelerating the analytics against that data using Swarm, Postgres, and the hardware accelerators of choice. And the beauty of this is that we're able to continue to use the standard interfaces from those systems and the standard interfaces to the analytics and BI reporting and dashboarding tools such as Tableau or MicroStrategy or Qlik or any kind of custom application. And because we're using Postgres as the sort of core environment that we're doing the acceleration against, anything that can access and talk to Postgres or Postgres interfaces, we run against. There's no changes, there's no additional drivers, there's no additional interfaces, there's nothing really to change in the environment. It's as close to plug and play as you can get. Next slide, please. The way that we do that is Postgres has a really nice, well-defined interface. It's called Foreign Data Wrapper. And we hook into that with an extension, and we overlaid that data, that the extension as an integration to Postgres and where we drive the hardware acceleration in the servers. Again, standard tools and interfaces, so your applications don't change, your queries don't change. You may want to optimize it because of some of the things that we do give you better performance under certain conditions. But by and large, those queries, the interfaces to your application, all the tools that you're going to use, monitoring tools and interfaces to other existing tool sets remain the same. And we can run in cloud or on-premise servers, data storage. It doesn't really matter where. There's nothing special about the file system that we need. And so we can, again, integrate into just about any kind of architecture. Next slide, please. Thomas showed you a slide a little bit back about comparing Postgres to Postgres Accelerated. We actually have taken and we're running benchmarks against well-known data warehouse solutions that fit into our market. And Greenplum is a good example of that. And if you're familiar with TPC-H, there's a couple of different kinds of tests that get run. One is just a power test, and we're a few minutes faster there, but that's just how much can I run queries one right after the other, and how long does it take? The concurrent users test is much more real world, and it is multiple streams of queries being run against the data set. And in this particular case, we're almost twice as fast as Greenplum. But the most significant thing to take away from this is what it costs to do that. For an equivalent set of resources, hardware resources, storage, server data, memory, all those sorts of things, it's about a €3 TCO that's about a quarter of a third or so of what you would be, the investment that you'd be making at Greenplum to achieve the same results. So we find that for a nominal investment, of resources and software integration, then it's a very nice TCO, something that's very valuable to an organization. Next slide, please. So it's actually, there's a little bit of work. You got to get an FPGA equipped server. Fortunately, these cards are all designed around the PCI Express bus interface. All traditional servers being built today, running in data centers, have that interface. Even my laptop has a PCIe bus. So that's pretty simple. Plug the card in. There are a couple of things that you might do to the schema that you have. It's I described earlier the interface to Postgres is via foreign data wrappers. So you create a foreign table. These become swarm tables. These are the data. This is the data that we're going to manage in the environment for providing the acceleration that you need. We're going to format that data in a way that makes sense to us, so that when you run queries against that data and the queries don't change, select star from foo, then it would be driven by the parallelization that we provide, and also get driven against the FPGA directly. And I'll talk a little bit about what we do on the FPGA. And there's no changes to your code. Again, this is the application code. There's no real changes to the SQL that you run, the queries, the DML that you would run in your application. There could potentially be slight changes that you need to make into your schema, and you might want to make some changes to your data model, but there's slight. So it's a very, very simple migration from standard Postgres to an FPGA-driven system with Swarm. Next slide, please. So one of the things that we do quickly is inserting data. We actually get a pretty dramatic insert rate, and as I described here, we're 20 million records a second is not unusual. Now, the way that we do that is that we pack the data and send it basically over to the FPGA. So as data is brought in, we send it into the foreign data, the foreign tables that we manage, and it's pushed over to the FPGA, where the FPGA is actually doing the work of compressing and packing the data into the format that we're going to be storing it on disk, and finalizing it and pushing it onto disk. And so it literally, as the data comes in, a little bit of formatting, queuing, handing it off to the FPGA to do the work. The compression and the data format that we use is really kind of part of the significant data performance improvement. They're somewhat cumulative, and I'll talk a little bit more about that in just a moment. But it's important to note that this is all happening on the FPGA. We're not burdening down a CPU for doing things like compressing and pushing it into the storage subsystem. Next slide, please. So where we have, you know, back to the query example that Thomas pointed out, where we do a select from where things of this nature, you know, this is a fairly traditional query example. So we're going to select from a particular table, and we might have to scan the table. We may have indexes that we read. This is levels of indirection from an I/O standpoint that you have to start factoring into how your system is running. You know, the picking of the rows, the picking of the columns, packing up the result set is, you know, fairly well explained. And this all happens typically on a CPU. Next slide, please. Column store example, I'm not going to rehash what Thomas described, but this is similar. Column store is an attempt, it is a architecture that is used to optimize analytic, primarily optimize analytics processing. And so in those cases, you'll quite often find where you have an OLTP system and an analytics system. If there's any level of integration, you may end up with multiple data being stored in the database at the same time. Where an OLTP data transactional inserts needs to be transformed into a column format for analytics. Column stores are not very well suited for OLTP type of transactions, and so we either need to make that part of the overall system or an architecture that separates these things out. Next slide, please. Swarm takes a little bit different approach. We actually have a concept that we call optimized columns. And the optimized columns, you can think of those as sort of multidimensional indexes, but it's the efficiency that we, as we're processing these queries against the data on the swarm tables, we very quickly can reach into the table and get to the rows, the data that we need. In some cases, there's very few actual IOs pulling data off a disk. When that data does come off a disk, we pipe it through the FPGA, where it does compression and picking of the specific columns, the projection that we're looking for, the filtering of the rows, which is by and large already pulled off of the disk, and so we quite often are not always going back to the disk, but if we have very large data sets, it's a very efficient process. And we pack the result set back up into a package that we pass back off to the CPU. So all of the work from getting the data off of the disk, compression, picking of the columns, packing the result set, and sending it back to the CPU is all done on the FPGA. We get a very effective throughput, and we call it effective throughput because of the compression and decompression factor. We can actually optimize IOs across the storage subsystem or across the network if we're doing network-based storage. And so all of this gives us the kind of performance as we described earlier in some cases 6 to 7 overall on a TPC-H benchmark, or in some particular queries we're up to 50 times faster depending upon the type of query that we're running. Next slide, please. So kind of the core features that we have, again, store and analyze very rapidly. We support all common data sources. You know, it's not so much that you have to optimize that particular data source, because when you're doing the data analytics architecture, you quite often are moving data through an ELT process. So we integrate with all the common ELT tools. So we can pull data from just about any source that you can think of. We support all the extensible data types, including geospatial, JSON, and so on. And the beauty of this is that we can interactively explore and analyze data, in some cases in near real time as the data is coming in from a transactional system. And the separation of compute and storage, meaning we can run on-prem or on the cloud or network attached, direct attached, it doesn't really matter. Give us the performance architecture that we can scale out on. And again, it's a drop-in integration and placement as possible. In effect, open source databases, we use 100% standard interfaces. There's nothing particularly proprietary about how we integrate with the rest of the world. So, next slide, please. Here's an example of actually a customer that we had a challenge with. It's a leading consumer loan company in Europe, and they process their enterprise data as the data comes in. They move it into a warehouse environment where they do data mining and reporting. They need to move that data. They needed to move that data in a particular maintenance window, and they were running into the situation where their data was growing, the number of transactions and users, and their business was growing so much and so fast that they couldn't meet the SLA of getting the data into the warehouse. So we were able to very quickly identify where the bottleneck was and provide them with a solution that accelerated the data processing pipeline, got the data into the data warehouse quicker at a fairly low cost, low risk integration to their existing Postgres systems. So it was a very quick return on investment that were weeks from the project start. And they are now able to process twice as many loan applications per day. So that translates into a very rapid increase in the amount of volume that they have. And they're able to continue to meet those data warehouse or the maintenance windows for getting the data into the data warehouse. So not only did we solve the ELT problem, but we also gave them better performance on the analytics overall. And they were able now to look at their data in ways that they weren't necessarily able to look at it before because of the performance characteristics. Next slide, please.
Okay, so thank you, Skip. We're at just actually past the 45-minute mark, so we'll still take a few questions. There are a number of them here. Before we get to that, just invite anybody who's interested in trying Swarm 64 or would like to have another follow-on discussion about your specific requirements to get in touch with us via the website or email us at info@swarm64. A couple of questions. First one I'll take, as predicted, someone asks whether they can get a copy of the slides. The answer is yes. We'll email everybody who signed up for the webinar with a link to the slides and a recording of the event, so you can share it with others or view any part that you may have missed. Next question, I think for, actually I'll just give these all to you, Skip. This one, you mentioned we work with Xilinx and Intel FPGA boards on premises or in the cloud. Do we, person wanted to know if we support the Amazon F1 server, their FPGA equipped server.
Our cloud strategy is spinning up very rapidly, and between Xilinx and Intel, there's a number of hyperscalers that are supporting FPGA instances. So we have a pretty aggressive campaign underway right now to move into the cloud as quickly as possible. We expect to see by Q3 going into Q4, we'll be on on a handful of the larger cloud providers that are using FPGA instances, and Amazon included, yes.
Okay. Next question, is there a Postgres version requirement?
Interestingly, no. And that's the beauty of using a tool like Postgres, is because they have well-defined interfaces that we plug into, so we do not do anything to Postgres itself. There are maybe some slight configurations, recommendations that we have in our installation guide from the installation standpoint, but we don't fork Postgres. We don't require a specific version. We support the 9.6 and above. We currently are deployed against 11. We have 12 in the lab, so when 12 ships, GA will be right there with it. And you'll be able to take advantage of, and with Swarm, take advantage of the feature functionality introduced into 12. And this is the beauty of this. We work closely with the Postgres environment, the community, so that we're making sure that we're anticipating new feature functionality and analyzing that to determine how we can take advantage of that and accelerate that as well.
Okay. And last question, and this answer this might depend on the data. Might vary from user to user, but we're asked, how long does it usually take the FPGA to compress and decompress data? What kind of, how long does that usually take?
Let me take that one. What you're really looking at is more a bandwidth question. So FPGA always decompresses on query. This allows you to store and cache data at all times compressed, which is a great value. So every single query decompresses, and there you're looking at a bandwidth of double-digit gigabytes per FPGA card. And that then slightly depends on which vendor card specifically, but you're looking at double-digit gigabytes of decompression. And similarly, as data gets pushed in, we're usually looking at these 20 million rows that Skip was mentioning earlier. They usually tend to correspond to something 1.5 gigabytes per second inbound data, which is a very large amount for any database. Usually they are around 1 million rows a second, which is usually something in the 100 megabyte range. We're able to, in a consistently transaction-safe manner, handle 1 to 1.5 gigabytes of raw data coming in every second, in addition to the double-digit gigabytes we decompress. So that's roughly it. We're looking at compression capabilities for 1 to 2 gigabytes, decompression capabilities for something much more in the line of 20 gigabytes, depending a little bit on the individual card. And that is per FPGA accelerator card. So depending on your setup, it may even be sensible to put multiple cards into your server or look at a scale-out solution.
Thanks, Thomas. All right, and I think we'll end there. Sorry, we've gone a little bit past the 45-minute mark. I want to thank everybody again for joining us today, and hope you got a lot out of it. And thank you to Thomas and Skip for sharing your expertise, and look forward to seeing all of you on a webinar again in the future. Thanks again.